Another tree-based data structure we are going to learn is a heap. A heap is a binary tree. It's not binary search tree. So binary tree means a node has at the most two nodes. In addition to that, to be a heap, we need to give two more requirements. The first one is the tree, binary tree should be almost complete from top to bottom, from top layer to bottom layer, and from left to right. So if you have only one node, so this is a binary tree as a heap. If you add the second node, it should be on the left, so it should be from left to right. But if you do on the right, this is not a heap. And the third node should not be added here. So third node, you need to complete the given layer first. So this is a heap, but if you add here, that is not a heap. So just to continue, so tree should be almost balanced or complete from top layer to bottom layer. And then if the given layer, the last layer is not complete, it should be from left to right complete. So something like this is a heap. So here, if you want to add one more node, that should be this node. Since it should be from left to right, the bottom layer should be complete before you add one more layer. Now, if you add one more node, it should be here and the like. Now, if you want to remove a node, so this node should be removed so that we could keep the tree balanced. And then if you remove again this one, remove again this one, and the like. So that is almost a complete requirement of heap. And the second one of a second heap property is that each node stores a value that is greater than all the values in its left and right child. So given any node, root node, you have a node on the left, nodes on the right. So this value should be greater than any of the nodes, both in left and right. Remember, binary search tree, this node should have a greater value of a left subtree and but smaller value on those in right subtree. That's a binary search tree. But heap, it should be greater than any of the nodes in both. So that's a heap. But here, that is called the max heap. But if the node stores a smaller value than any nodes in the left and right tree, that is called the min heap. So properties are just the opposite, but the other, all the operations or implementation would be exactly the same, but comparing the values different. So in this lesson, we are going to study max heap only, but if you need the min heap, we can easily convert that though. So that's the two additional requirements of a binary tree to be a heap. So heap is something like this is an example. Add any node, choose any node, then left and right, the node has a larger value than any. Pick up any nodes, and left and right is there. So in this definition, there's no notion of a sibling ordering. Sibling ordering means for this parent, you have two children. So which one should be greater, left or right? We have no requirements for that. Any order is fine. Left could be bigger or right could be bigger for this one. So sibling ordering is not requirements. Only the parent should have a greater value than any value in its children. That's the requirements. Then how we can insert a node onto the heap. So insert algorithm, let me explain by example. Suppose this is given heap and then we want to insert the 40. Then we know that it has to be almost complete. So the only place we can add a new node is here. The last layer and then left to right. This is the position to add a new node. So have a place for new data 40 there, but do not store data 40 directly. So second heap requirement is that parent should have a bigger value. So just make a room for a new node, then compare with its parent. So parent is smaller, then store parent instead there, and then new data should be stored in the parent instead. And then keep comparing with the parent again. Now the new data 40 has its parent is 25, so 25 is smaller, so 25 should be stored here, and this is a place for 40. Now compare with the new parent 80, that's bigger, so this is the right place for 40. So begin with the last leaf to make the heap balanced, and then compare with its parent. If a parent is smaller, just keep the parent instead. So climbing up the tree until its parent is bigger, then that's the right place. So that's how to insert a new node. How to remove is in heap, removing is only at the root. So root has the largest value in the heap. So remove from the heap means you want the largest value from the heap tree. And then the heap does not define an operation that you can remove data in some arbitrary location, only from the root only. So we need to keep the balanced tree after removing the root. So the algorithm would be as follows. So let me explain by example. Suppose this is a given heap, and then remove means we are going to remove 80. So data 80 is retrieved, but we do not physically remove the root node. If we remove the root node physically, the structure of the tree gets corrupted. So we want to keep the structure. But to make the tree balanced, heap balanced after removal, so we need to remove physically the last node only. So remove the last node instead, but keep the value the 4 at the root. So that's the first step. So read from the root 80. Instead of physically removing the root, remove the last node, but keep the value in the last node in the root. And then adjust the data so that we keep the second property of the heap. That is, a node value should be greater than any children values. So compare with the children, the value at the node is smaller than whichever is bigger. That is 57. So 57 places the root node, and then this value goes down. So swap those two. And then at this moment, compare with the children, whichever is bigger comes up, and then that value goes down. Now this one has no children, so this is the right place. So this is the remove algorithm for the heap. So next videos we are going to implement the heap data structures.